Welcome to this session. This is a two-part session. As you know on your program, we're going to start now. All morning we're going to go till lunch, and we're going to be talking about TCP. Okay, so this session is named TCP Tips, Tricks, and Traces. Now, intentionally, the first session, if you notice on your program, it's a one fin. So beginner level, we want to go in and talk about some of the TCP fundamentals. I noticed on some of the other sessions that even I attended, sometimes the instructor might say, hey, you know, it's just a window problem, okay, moving on. And if we're new to TCP, we're going, whoa, no, what does that mean? Or no, it's, you know, no big deal, SAC, you know, okay, there's SAC, there's this bit, there's that bit, and it's like, whoa, time, back up, hang on. What is that? What does that mean? How does it work? So we're not going to make any assumptions as far as your level of TCP experience and knowledge. We're going to spend this first session, one fin, going through those fundamentals and making sure that we thoroughly understand them. That way, in the second part of this session, when I start throwing some case files some case studies and showing you some of the things that I've seen out there, you can follow along and understand better what's happening. Okay, so to just introduce myself, you see my name there, but okay, my name's Chris Greer. I work for a company called Packet Pioneer. So I basically do consulting using trace files and Wireshark, and I also am a Wireshark instructor. So a lot of times people, they'll be having a problem, they'll find me through whatever means, sometimes my YouTube channel, sometimes the website, or different blogs that I do in the industry. They'll have a problem, sounds kind of like what I wrote about, and they'll contact me and say, hey, I got a problem, can I send you a trace? I just got a query last night for somebody in New York that's having a performance issue. So I'll do my best to help them out, and sometimes that'll turn into a Wireshark training class, which is great. So they'll say, hey, that's awesome, but how do I not call you again? So in a way, I'm kind of training myself out of a job, right, with the training part, but hey, that's what I like to do. I like to instruct as well. As I mentioned, my YouTube channel, go out there and check it out, youtube.com/packetpioneer, or if you just search for Wireshark or filters or that kind of stuff, you'll probably find it eventually. What I try to do on my YouTube channel is not do anything longer or much longer than 10 minutes. Because, I mean, let's face it, I have a tough time sitting through a 1 hour or hour and a half full. Even the Shark sessions, it's just I have a hard time finding that time to dedicate my brain to what's really happening in that video. So what I try to do out there is just I'll call them shark bites, even though tomorrow we have shark bites technically. But I try to just throw an idea at you. Here's a 5-minute, that's all we're gonna cover. And then boom, 5 minutes, 10 minutes. So if any of you guys are out there who have seen those videos, please come up and chat with me on one of the breaks or afterward. I'm always interested in ideas or things that you might be seeing out there that would be useful to have a video for. Sometimes I create those videos on behalf of my customers so that they can better explain what's happening in their trace file using that video. So for example, I say, oh, you just have a receive window problem. And instead of them needing to go to their boss and say, hey, we've got a receive window problem, instead they can watch that 5-minute video together, and you know, then I do the heavy lifting for you. So anyway, I'm absolutely open to suggestions in that way as well. Okay, what are we going to cover? We're going to talk about why TCP is such a critical protocol. Why is it something that, hey, a lot of us are in here, we're interested in TCP, we're interested in how it works. We're interested in how it delivers data. We're interested in looking at one of those screens like we've seen over the last couple of days, and the instructor stops and says, okay, you see the problems right there? I don't know, maybe you like me, when I first started coming to SharkFest, I'd sit in those sessions and I'm looking at the screen and I'm thinking, honestly, I don't see what's going on. And they're just running through this trace, and I'm just like, wow, okay, maybe one day I'll get there. Well, if that's how you feel sometimes, I mean, hey, I feel that way too sometimes at these sessions. You know, especially when someone's moving through a trace really quickly. So what I want to do today for you is to get you a bit more comfortable with what TCP does, how it works, some of those underpinning things that we should know to then be able to build on later. Okay, so we're going to be talking about the handshake, options within the handshake, TCP windows, both receive and congestion. We're going to be talking about retransmissions, how those work, selective acknowledgements. Okay, so some core things. Now, you might know some of this pretty well. You might know it cold. But I think an important thing with TCP, and one of the reasons why you see a lot of these instructors do what they can do here up on this stage, or even with a trace file, if they are sent a trace file and they can just like Hansong, he can just rip through and go, oh, 30 seconds, you know, he takes 30 seconds and bam, I found the problem. It's because he knows the fundamentals really, really well. He knows them cold, right? He knows how it's supposed to work. That way when he sees a trace file that's struggling, having some problems, he can more quickly spot the problems in that trace. Okay, so that's why we're doing this today. We're going to go over some of these fundamentals and then make sure we can really understand what they're doing. Again, this is in session 1. As we get into session 2, we'll do a bit more with case studies. Also, tips for isolating performance issues. This is the TCP tricks part. So creating a TCP profile. In Wireshark, how can we create a profile that can help us to find some of these issues faster? What filters can we set? Spotting delays in TCP streams, so I've got a handful of things there for you. And of course, case studies like I mentioned. All right, so first of all, TCP, why is it a big deal? What's the reason why we're all here? Why are we interested in TCP? Well, important stuff uses it, at least for now, right? So it's reliable, it's connection oriented, it's going to ensure that that data gets over there and we get a positive acknowledgement. Our stuff got there. Also, TCP handles loss and congestion relatively well. If TCP is smart, it can figure out, okay, I just sent some data on the wire, I sent it at a certain rate, I started to sense some congestion, I saw some loss, let me back off a little bit on how much I'm sending. It wants to figure out, especially with a large data transfer, it wants to figure out what's the best rate that I can send this at without running into problems. So TCP is a smart protocol. Now, how it does that and interpreting what we see on the screen, that's what we're here to do today. Now today, I think the number one reason I get called anyway from my clients is because just stuff is slow, right? We all hear that. I still haven't ever gotten a call from somebody telling me things are too fast. This is probably why they point the finger at you. Could be why you're here at SharkFest. No doubt, this situation has led you to look at packets, right? As we're going to go on to talk about, from a network engineering perspective, a lot of times we just get the blame, don't we? And if we don't get that, if we are not to blame, then a lot of times the onus is on us to show who is to blame, right? It used to be 10 years ago, we could just say, it's not the network. My stuff's great. Not anymore though, right? Now we need to facilitate the next step of troubleshooting. Okay, if it's not the network, then what is it? Right, so back to us, back to network people. By the way, network people, raise a hand. If you are from the network side of the house, hands up. Woo! Okay. Server people, application developers, we got, hey, man, raise the hand, buddy. You're good? 2, 3, 4-ish? Wow. Notice who's coming to SharkFest. I mean, it's great to have you. Awesome. But yeah, so network people realize we're the ones that have the feeds. We're the people that path the packets on where they're supposed to go, right? So we're responsible for collecting them, capturing them, and understanding them. One time I was working with one of my customers who grabbed the trace file. He's a network guy, right? He's able to download Wireshark, put it on a box. He gets it in the path of packets, which is a whole other conversation. gets in there, grabs a trace file, looks through, doesn't find any retransmissions, and he figures, well, my network's fine, it's not me. And then he emails that trace file to his application guy. So I said, okay, what happened next? I know you just sent it over this wall to the other side of the house, but what happened? I mean, what did he do with it? He says he didn't know, so he goes over there, talks to the application guy. So what'd you do with it? What'd you find in those packets? What'd you find in that trace file? Applications guy, I don't know what that stuff is. That's all your stuff. I deleted it. PCAP? The heck is a PCAP? Right? So I was like, well, clearly that didn't have the desired results. A lot of times if we grab a trace and we can't quite figure it out, or if we exonerate the network and then send that trace to somebody else, sight unseen, that's not going to do a whole lot of good, right? Network people are here today. That tells us something. Network people, we're responsible for owning the packets, collecting them, capturing them, and sorry, understanding them. Now we come, when a problem strikes, okay? OSI model on the right. Hopefully you have seen that OSI model before. When it comes to network engineers, if we're from the network side of the house, which most of us are, I grew up in the network side of the house. If a problem strikes, our goal is basically, and for all intents and purposes our responsibility, is to exonerate the lower three layers. We might put a little toe up into the transport layer with firewalls, but really when it comes to those lower three layers of transport, cables, switches, routers, making sure data can get from there to there reliably and with low latency. If they go down to HR and they pull your job description, and there is a legitimate problem in those lower three layers, that's me, right? Hey, if there's a problem with Wi-Fi, if there's a problem with the switch fabric, the infrastructure, if I'm legitimately dropping traffic, okay, you got me. It's a network. So when a problem strikes, think about what your knee-jerk reaction is. What tools do you go to? How do you exonerate your part of this whole thing? Maybe you go and get a throughput tool, maybe you run some other tests, maybe you go over to some monitoring platform and you take a look for any red and horrible indicators, packet loss. Do you have an interface that's flagging drops, discards? So if we don't see that stuff, we go up to our monitoring solution, everything looks green, it's SNMP based, I got NetFlow over here, I don't see high congestion, I see low latency, I see things are up. Looks good to me, right? Then you tell them, hey, it's not my network. Well, we still got the problem. Okay? So we go to the other side of the house. Server peeps. Pull out their job description, and let's just wrap those upper layers together. Let's call that just upper layers, session, presentation, application. They're in the server, the app, the virtual environment. They go in there, they check their resources, they look at make sure nothing's spiked, no weird process, no backups happening. They go in there to their little world. To be honest, I don't have a ton of exposure into that world because I'm not a server app guy. They go in there, they check their stuff, and they say, hey, resource looks good, don't have any spiked processes, memory's all right. It's not me. And what do? Well, they dump it right back onto you. This is a network problem. My stuff's great. Do we notice a layer that neither side is really taking ownership of? This whole conversation came because traveling around, talking to people, helping to troubleshoot issues, this is what I see over and over and over again. Sidebar, I'm not saying all problems are in the transport layer. I'm not saying that. What I am saying, though, neither side of this house, I mean, IT has become very siloed, right? You're this kind of expert, that kind of expert. You're app, VM, network, Wi-Fi. You have all these fields of responsibility. But where's the TCP guy? mean, think about it. Your company is running mission critical. If anything happens to these applications, if they slow down, drop, can't connect, we're in big trouble. These applications are using TCP, but who's the TCP guy? I'll sit down in a conference room with a whole IT department. So who owns TCP? No hands. Like, there's that redhead stepchild that no one really wants to grab and own. So the fact that you're here at SharkFest and the fact that a session like this caught your attention means that that's now you. You're the TCP guy or girl. And you know what? Grab it, own it, live it, breathe it, become an expert at the transport layer. Why? Because you're going to be the one that can fix some stuff. You're going to be the one that can answer the unanswerable. You're going to be the one that they go to, like, hey, that guy got that thing real fast last time. Let's go back. Where are they? Where's the packet person? Right? So for me, personally, in my career, that's why I started focusing on the transport layer. I started getting deeper and deeper into this protocol because that's what I saw. It's like I go into an environment, you got the Microsoft guys, you have the app server people over here, you have these like CCIE hotshot Cisco guys over here, and everyone's fighting and we can't figure out the problem. And then these packet guys walk in and they're just like, whoa, boom, there's the issue. And it was a TCP thing. So inside your brain, as far as what you are responsible for within your environment, if you're a physical data link network, let's reach up, grab that transport layer and own it. Now, what you're going to run into, one of the reasons why as network people we say, you know what, that's above me, is because that TCP component and everything that it does is within devices that we don't own in many cases, right? Where is the TCP stack? It's inside that box there. My network can't do much with it. I don't have the responsibility for shaping it or changing it. It's not generated by my network. However, to push forward as far as being analysts, it's something that we want to own. So if you find this in your environment, it could be, this is something that we want to grab hold of. Okay, so let's go ahead and start digging here. First, how does TCP start its conversation? We've seen it so far today. First thing we got to do is handshake. All right? We're going to spend some time talking about the TCP handshake. What's in it? What can we learn from it? Those first 3 packets, which are so critical, we've heard that from sessions previous to this one. Make sure to get the handshake. Make sure to get the handshake. Okay? We're going to take a look at a couple of trace files that have some handshakes, see what we can learn, look at those options, see what they mean. And we're also going to look at a trace file that was missing a handshake and see what we are missing from that stream. What can we not tell about that conversation because we missed the handshake, okay? That's where we're going with this. Now, to put it simply for you, this client wants to talk to that server. It wants to get something from it. It wants some piece of information. Before it can do that, it's got to do its handshake thing, right? 3 packets, TCP SYN, SYN-ACK, ACK, and then it can go on and do whatever it was it wanted to do. Hey, give me that picture, give me that file, give me that thing. Okay, here you go. So those 3 packets, that's where we're going to focus. Now, if this is review for you, great. If there's something you can contribute to what I'm doing up here, hey, I like this part of the handshake too. Cool. But this is meant to be review for you. Okay. Enough PowerPoint. I'm not a PowerPoint guy, so. In fact, this morning I opened up my presentation and I found that every single image that you see on this presentation was missing. It was gone. From the shark fin to everything you see. So I had to rebuild it back there about an hour ago. Anyway, okay, let's go ahead and go to our handshake. So let me get set up here. Okay. All right. So first, when it comes to Wireshark, okay. Now, something that I always need when someone else opens up their Wireshark is I need them to talk me through their screen. Just talk me through what you got here, talk me through your profile. So I'm not going to assume you've seen all these columns and all that stuff. But basically, so for me, I like to create, you can't see it down here, it says TCP plain. This is just my plain Jane default TCP profile. As you can see, it's not that fancy. It doesn't have a lot of extra information in it. If I need all that other stuff, cumulative bytes, calculated window size, bytes in flight, if I want all that stuff, I can flip my profile. But at first, sometimes that stuff makes me dizzy. All right? And especially when I'm looking at somebody else's screen. You know, I see what all the columns they have, and I'm like, whoa, okay, hang on a second. That's also for me, sidebar. Sometimes in my classes, people will say, oh, you know, show us your profiles. Like, what kind of profiles do you have? And so I'll bring up my profiles. I'll go, oh, there's all my profiles. Oh, can we have those? That'd be great. No. You can't. Why? Like Hansong said yesterday, this is my way. And in my world, in Chris land, it's my way or the highway, right? This is how I analyze my setup, my configuration. Unless you built all of those profiles, how do you know what they do? Right? So that's for me. I tell my students in my classes, don't use anybody else's profile. Build your own, because then you know exactly what you did. Right? So for me, I've got TCP plain, I've got TCP advanced, I got TCP Windows. Depending on what I'm troubleshooting, I'll use one of those, at least first, right? And then we'll go off into the specific protocol stuff. Now let me tell you a little bit about TCP plain. Now for me, one thing that I like to do that's not default, for me, I used to hate the colors, so I just turned them off, but I started getting used to them and they grew on me. But you'll notice one thing for me that I like to do is I like to paint the sins green. See, up at the top. So one of the first things I do, go into my coloring rules, I create a new coloring rule, paint it bright green, tcp.flags.sin equals 1. Okay, that'll paint all of your sins 1. Or paint them green. I want to see them. I want them to jump out at me. That's a personal preference. Also, as you've heard in other sessions, delta time. Okay, so I like to add a delta time column. I like to do that almost for every single profile I have. Hopefully that's something that you have in your profile as well. Now to quickly do that, I know we saw that yesterday. I just want to make sure I don't want to leave anybody out or behind or anything. I'm just going to go to my preferences. I'm going to go to my columns. I just like to manually add it when it comes to delta time. So I add a column called delta time displayed. Okay? I move it up next to the time column that I can then change to running total or time of day or whatever, but that delta time is an important one. I'm not going to talk about this right now. In fact, I'm just going to kind of close it up a little bit. This up here, it says time since previous frame in this TCP stream. Now for this trace file, this is one TCP stream. So that column and the delta column are the same. All right? So you might be thinking, well, Chris, why do you have a redundant? It's the same thing. Because I'm going to get there. I'm going to show you guys why you would want to add another time column and how that's useful for you in spotting delays. But, okay, just going to kind of close that one up for now. Okay, so let's do a little bit of digging. So that's my basic TCP plain setup. I also do have some buttons up here. Bad TCP, no broadcast chatter, slow HTTP. I've got a handful of other ones. But basically, those are my quick filter buttons. Okay, so SYN. Let's take a look at this handshake and let's see what we can learn from it. Okay, so the client has initiated a SYN to the server. This is port 80. Let's go ahead and take a look at what we can learn. Now, hopefully everybody can see this. I'm going to blow it up just a little bit more. All right. Okay. Layer 2, going to jump it. Layer 3, for now, I'm going to jump it. We see our IPs. Let's just take a look at TCP and what we can find here. All right. Source port, 61330. High client-side port number, dynamic. Client-side ephemeral port. I'm not too worried about that right now. It's just a high number port. Great. Destination port, the guy I'm going to talk to. Stream index. Now, Wireshark does a nice little thing. You notice, maybe you've heard this in a different session, but anytime you see a value that is in brackets, those hard brackets, that is a Wireshark value that it has done. That's not part of the data. It's something Wireshark does to help us interpret what we're seeing. Now we see here stream index 0. So this is the first stream of any kind that we see in this trace file. If I saw a SYN and a SYN right after it on a different port number, that'd be stream 0, stream 1. Right? So you can quickly spot how many different TCP streams do I have in this trace. We can go up and look at conversations if we want to. TCP segment length. How much data is in this packet that I'm sending? As we see, none. Sequence number, 0. We're going to talk about sequence numbers and how to run through that and how sequence numbers work. But basically, what Wireshark does is it will start this sequence number off at 0 for me. If I select that field, let me go to sequence number. I'm going to come over here to my hex. So a sequence number, just to boil it down, a sequence number is a number that increments as I send data. Okay? If my sequence number goes up by 1, it's because I've sent 1 byte of data. All right? If it goes up by 100, then I've sent 100 bytes of data. I've got a positive acknowledgement back for that data. It allows TCP to figure out what actually got there, where am I starting from. In this, in the packet train as it leaves, what's missing, how do I fill that back in? That's because every byte that I send has a sequence number assignment, if you will. We're going to look at how to count that and how that works in another trace file. But Wireshark figures, well, by default, as human beings, we have a better time starting off at the number 0 than we do some long, crazy 4-byte number. If I select the sequence number value here, look at my hex. That's actually a 4-byte number, 65B4940E. Is that 0? No. That's an actual big, long, scary looking number. But as a human being, I have a tough time making that number my starting point. Right? I like things to start at 0, and then it's easy to count up, and I can see how much data went and how much has been ACKed. For that reason, by default, Wireshark will do relative sequence number, meaning, don't worry about that long, crazy number, Chris. I got you. This is just going to start at what we'll call 0. Now, that's something that I can take off if I want. If I want to see that original starting value there, that's a TCP setting. I can always bring it back if I choose. I just right-click TCP, come into protocol prefs, and then I can come down and I can uncheck relative sequence numbers. That'll make that scary number come back. Now, some people would say, that's the one I want to see. Boom. For me, it's a long, scary value that it's just more work for me to do. I'm all about making less work for myself. So let's go ahead and turn on relative again. Okay, relative sequence numbers. There we go. All right, so what is the client doing here? The client is saying to the server, this is my starting initial sequence number. This is where I'm going to begin. I'm not telling you how much I have to send to you yet, but let's just start from my perspective. I'm starting here. Now the acknowledgement number If we look over at our hex values, this is also a 4-byte value. At this point in time, that acknowledgement number is zeros. Why? Because the server hasn't sent anything to me yet. He hasn't told me where he's starting in terms of his sequence number on his side. I'm just telling him where I am starting. This is my initial sequence number value. Sir? The question was, does that depend on where you take the capture from? Great question. It can. Yes. That can depend. Do I have a box in the middle that's changing it or taking over that part of the TCP header? That's possible. So that's also another reason why it's nice to have client-side and server-side captures simultaneously, because you can see what was let go, how did it arrive, what was let go on that side, and how did it arrive. I wrote an article back a couple years, and I'm going to show you guys the trace file that it came from. And it was like, and I said, hey, network, leave my packets alone. Because so many network devices now can muck with that stuff. So that's a good comment. But if I don't have anything on the network that's changing this stuff, that's the whole point with TCP. So he's saying, hey, this is where I'm starting from a sequence number perspective. There you go, server. You go ahead and tell me what you have on your end. In fact, the SYN, the whole reason why it's called SYN, let's synchronize this stuff. All right, here's my sequence number. You send me yours. We're synchronized. Now, let's come down here. Okay, window size value. All right. Now, window size value, this is an advertisement of what my receive window buffer is. How much can you send me at once? Yesterday, Hansong used an example. I thought this was really cool. With the pipe with water in it, and we have a bucket on each side. If you're going to send me a bunch of water, how much can you send me at once through that pipe, and I can catch all of it, right? So I'm telling you right now, I got an 8K receive window. Right now, at this second, that's what I'm advertising. Okay? Can't send me anything more than that. So this, in some cases, can limit the server on how much it can send. Like, really, Chris, you're only going to let me send 8K at once? Now, one of the reasons why this is so low, you might be thinking, 8K, why is this guy advertising something so low? Well, first of all, we do have some options down here we haven't talked about yet. But when a client is first initiating something to the server, it doesn't want to start with this massive receive window allocation. Because every time that I send a SYN, I'm committing resource to that connection. I'm saying, you know what? I'm going to allocate in memory 8K. That resource will be earmarked and stamped just for this connection. Well, what if I'm sending a bunch of SYNs to a server? What if I send like 10, 12, 14 SYNs to that server, and I start with like a 1 gig window? That's allocated. So my SYN could say, 1 gig window, bam. And I only have so much resource, right? So I'm going to kind of start small. Like, are you really going to pick up the phone server? Are you playing hard to get? What's going on over there? All right? I'm just going to send out a SYN. If you respond, I'll work with that window. I can adjust it. We'll work some other magic so you can send me more than just 8K. Calculate window size. We'll get there. Options. Let's talk about some TCP options. Okay? So this is also where I am basically laying down some ground rules in the relationship. Okay? So I'm saying, hey, server, I can only receive 1460 bytes in the TCP payload. Don't send me any more than that. I'm telling you how much you can send back to me in one packet. Okay, that's at 1460. We're going to talk a good bit about that as well. No operation, no operation, no operation. Whoa, so do I just have a repeating myself problem here? I mean, what's up with all these no operation TCP options? Is that a problem? Is it an issue? No op. Well, basically, let me explain that real quick. So TCP no operation, up here I'm saying that my header length is 32 bytes. All right, it starts there. Header length is 32 bytes. So that's it's a binary 8. If I multiply it by 4, I get to 32. So that number has to be a multiple of 4. A TCP header in terms of bytes is always a multiple of 4. Okay? Now when it comes to how I'm advertising options and making enough space for these conversations to happen, sometimes I need to pad the options field out to make that minimum header size that I'm the one who set it up there. This header is 32 bytes. Sometimes my options don't neatly fit into these buckets to make it a complete 32 byte thing. So what no-op does, it's completely benign. If I come over here, I'm just going to select no operation. You see, it's just a 1. Option value 1. It just means, hey, my maximum segment size, that's 4 bytes. No operation is 1. If I come down here on my TCP option window scale, you see my window scale, that's 3 bytes. My scale options, that's all the space that takes in the header. I've got to be a multiple of 4, so I'm going to pad that guy out by 1 TCP no operation. Okay? It's just packing peanuts. If I come down to SAC permitted, that's a 2 byte option, right? SAC permitted, we'll talk about that in a second. That's only 2 byte indication in the header, so what do I need to pad myself out to 4? I need 2 packing peanuts. Boom, boom, no operation, right? So overlook it, but that's why you see that there in the options part of the TCP SYN. It's just to pad you out to meet your header length and make sure that it's a multiple of 4. Window scale, all right. TCP option, window scale. So this is where I tell the server, all right, you know that window, that receive window upstairs that I told you about, that 8K thing? I really want you to multiply that number by, this is the value I'm indicating. Thankfully, Wireshark does the math for us. It's a multiple 2 to the 8th, so we got 256. All right, so take that number I just sent you up there and go ahead and multiply it by this number. That will be my calculated window size. Now, why do we need that? Well, if we come up to window size value, look at the amount of space that was originally allocated for the receive window in TCP. That's only 2 bytes. Okay, so the most this value can be is 65,535. If it's just that value that I'm using to indicate how much you can send. I mean, think about it. The original spec for TCP, the old school spec that was actually written, does anyone know what year that thing was written? How old is TCP? The old school one. It's gone through some change since, but when? 83? A little older. 81, RFC 793, 1981. Okay? So in terms of outstanding data on a wire, back in 1981, they probably thought, boy, you'll never need more than 64K on a wire going in one direction. 2 bytes will do. Right? Back in those days. All right, so that's why we just have that 2 bytes. That's why this window size value, the actual number can only be up to 65,535. Well, later on, thankfully, some TCP options came around to greatly increase the amount of data that we can put on the wire, introduce window scaling. So if both sides of the connection can do window scaling and we can add this option, again, we're just laying down the ground rules of the relationship here. That's what the handshake does. Both sides need to be able to do it. So here I'm saying multiply me by 8 to take that 8K or whatever number I send up there, multiply it by 256, that's my real, true receive window. This is a big reason why it's important that we get the handshake. Because if I never got that window scale, it's only sent once, it's sent in the handshake, and never again. I won't truly know what the window scale is. All right. Moving through our options here. SAC permitted. All right, TCP SAC. We're going to get pretty deep in the weeds with TCP SAC, but basically what I'm saying, I can do selective acknowledgement. What does that mean? That means that, hey, Mr. Server, if you send me a packet train, if you send me 10 cars, and I only receive 1, 2, 3, 5, 6, 7, 8, 9, 10, I can indicate to you which one was lost without you needing to send the whole train again, or from the lost point after that. It's a way I can selectively tell you, I missed that block, I missed this block, I missed that block. Can you just intelligently resend the stuff that was missing? Okay, there's a quick TCP SAC. Okay, so there's our SYN. Now there's also some other interesting information we can get from that first packet of the handshake. One field that I like to use as well is going up to the IP header, come down here to TTL. Okay, the TTL is 128. Why would that be useful? Any thoughts? Number of hops. What does that tell me? Now keep in mind, for me, a lot of the time when I get a trace file, I'm not the one that captured it. I got to figure out, how did they capture it? Where did they capture it? What kind of device captured it? I got to figure that all out. You can do it from the packets largely. Sometimes I'll ask my customer, say, hey customer, what'd you do? How'd you get this? But just to put myself, a big part of analysis for me, and again, my way or the highway, I got to think like the analyzer. Where was this captured in the conversation? Where was I? What, was I client end? Was I server end? Sometimes I'll ask my customer, hey, when can you talk again? Oh, I'm busy all week. I can't talk until the end of next week. Okay, I got to do it all from the packets themselves. Now this is a number that can really help me figure out where the point of capture was. Okay? TTL, IP TTL. How does IP TTL work? Well, it's not time as in minutes, seconds, right? Number of hops. So this packet will die. The next router that forwards it, once it hits 0, so every router it crosses, this number is going to decrement, all right? 128 crosses the first router, 127, 126, 125, 124, 123. If it ever got to the point where it was 1, router decrements it, 0, die, kill. Hey, sorry endpoint, I had to kill your packet. ICMP message, sorry, TTL exceeded, or TTL expired. Now 128 hops, that's a lot of hops. You can get around the world in what, 15, 16 hops or less these days. So that's a pretty good hop count. I'm gonna safely assume this number can get all the way to the server. Now, what does a 128 mean? Well, TTLs typically, I'll say most of the time, start at these bit boundary numbers, 64, 128, 255. That's where this number begins, right? So by capturing a 128, either this packet has not been routed yet, and it started at 128. Keep in mind this number only goes down, doesn't go up. So one of two things is true. Either this packet has not yet been routed, or this packet started at 255, and I'm 127 hops into that path, and that's where I captured it. One of those two possibilities is true. Well, there's a third possibility. It started at 130. I haven't seen that in so long. This thing started at 128. Okay? What does that tell me? I'm client side, right? If this was 127, client's 1 hop away from me. 126, client is 2 hops away from me. Unless, there's an unless I'll put in here, unless there's a box between me and that client that's like intercepting the IP stack part of it and rewriting it, or putting in its own stuff, possible. However, typically, most of the time, you see a 128 on a SYN, you're client side, okay? That's also while I'll peek up to that TTL. All right, enough on the SYN. You see how much we ripped out of one SYN packet? This is great. Yes? Possible. See, the question was, doesn't that 128 mean it's a Windows server? Now, this came from a client. A lot of times, Windows will use 128s. It used to be, back in the day, that different operating systems would use all kinds of different TTLs, and you'd see them kind of all over the board, and you can fingerprint the OS from that. I've seen that steadily disappear as stacks have been more standard. I'll say that. A lot of times, network infrastructure devices will start at 255. Maybe they think they have the farthest to go. Like if you sent a ping from a router, a lot of times you can grab that and see a TTL at 255. But what I've actually started to see, if anything, the number of hops go down in operating systems. I see more 64s today than I used to. Probably because 128 is a lot of hops, right? If I'm going farther than that, I want it to die before it hits 128. So thanks for the question. Carrying on, let's just assume, we're going to make an assumption here. Let's assume nothing messed with our TTL, okay? We don't know that at this point, but let's assume nothing messed with our TTL. This is the SYN-ACK coming back. Look at our delta time, 105 milliseconds. That's my network round trip time. Sent my SYN, got a SYN-ACK back, 125 milliseconds. Go there to the TTL, IP header. I got this 111 thing. Okay, now I can just make a guess. It's an educated guess. To absolutely know for sure, I'd need the other server-side trace, but I'm okay with not having that for right now. Now, when a TTL goes to the server does not say, let's imagine the server received mine, I'm 5 hops away, it started at 128, he receives it at 123. He doesn't cut and paste my 123 and then put it in his packet and send it back. Whenever an IP stack creates the IP header, it always starts with a full TTL. All right? Whatever its number is. So on the server side, that number started at something larger than 111, and on its walk to me across routers, it was progressively decremented until I got it on the client side. So now I can make an assumption here that's I can make a pretty good guess, especially with a round trip time like that, 105 milliseconds. What number do you think this number started at? Again, assuming nothing's hijacking in the middle. 128. It could have started at 255. Unlikely. That'd be a lot of hops to go through. So how many routers are between me and that server? 17. Okay. Again, absolute 1,000% sure at this point? No, but 99.999. Yeah. We're there. Yeah.
Is the TTL always going to be a power of 2?
Question, is the TTL always going to be a power of 2? No. It can, you mean from when it starts? 64, 128, 255. Sometimes you'll see a 60. I haven't seen those in a while either. I mean, if you guys see them out there, if you see starting TTLs of something else, come give me a trace of it. I'd love that. I personally just haven't seen it in a while. So, okay, so there we go. It's coming at me. It's a TTL of 111. Great. I can just kind of put in the back of my mind, my server is 17-ish hops away, or at least it was for this path. I've got 105 milliseconds of round trip. I mean, this alone can tell you quite a bit of info, right? Now, let's go to the TCP header value stuff. Let's actually go down here and just see what this server is doing. All right, coming from port 80. All right. Sequence number. As we know, this is a long, crazy 4-byte value that's really hard to work with as a human being. So Wireshark says, I'll do the work for you. Let's start it at 0. Acknowledgement number 1. Now that first packet the SYN sent me was empty. It didn't have any TCP length to it. It was 0. Maybe you saw that in the SYN. The receiver of that SYN will increment the sequence number by 1, and it will acknowledge 1. Why does it do that? This is called our ghost byte. In the handshake, this is TCP's way of making sure everyone's on the same page. It's not a true byte of data, but the client sends me an empty SYN, and I ACK him 1. It's a ghost byte, not real data. It's a false 1, if you will. But it's a way of telling that client, I heard you, I'll increment you, we're cool. By the way, I'm sending you a 1, here's my starting sequence number. Just go ahead and note that on the client side. This is where the server is going to begin. Window size value, 64,240. That's what the server is allocating in its resources for this connection. Come down to options. Maximum segment size, 1460 bytes. Server's saying, hey, we're cool. 1460, I agree. You can send me that. I'll send you 1460. That's our maximum segment size for this connection. Window scale. 0. The server's saying, hey, I saw your window scale thing, that option. In order for you to do it, I got to do it too. All right, let's do window scale. But what you see is what you get. If I send you a window number, window size value, 64,240, that's what I mean. Don't multiply it. Don't change it. You don't have to do anything with it. That's my real number. Okay, so the server, it's allowing window scaling. It's just saying, I'm just doing a window scale 0. And then SAC permitted. Okay, so these options, if the server did not say SAC permitted, let's just say it's an older stack, which I have a trace file of. Older stack, sorry, we can't do SAC. Terms of the relationship, I'm not open to that. So the client can't do it. Question? Question was, window scale to 0, is that a problem? No, because the server, at least at this point, the server is just saying, I'm not going to use a scale factor. So the number that you see in window size value will always be my actual calculated window size. Now, a lot of times, clients aren't sending stuff to servers. Servers are sending stuff to clients, in most cases, depending on the type of server. So a server doesn't like to allocate a whole lot of resource to this connection. Right? This is a receive window value. So the server doesn't want to say, hey, I'll dedicate a gig to you. That's way too committed for this relationship. Like, whoa, you want to get exclusive here? I'm seeing other people out here. So you get Friday nights. So it's a much smaller value, right? It doesn't want to allocate that much resource for just this connection. Now the client side, it knows, hey, me and you, we're exclusive. Here's a scale factor, here's a bunch of resource I'll dedicate. All right? So is this a problem? No. In fact, I'd prefer this rather than no window scale, because if the server doesn't want to do window scaling, I can't do it either. So at least he's involved. He's letting me do what I need to do on the client side. Does that answer the question? Hopefully. Yeah. And in fact, okay, so I got a trace file. In fact, we're having so much fun that look at our time. Whoa, I only got 20 minutes. I got to move. We're going to talk about 0 windows. When that goes down to 0, what happens? All right, so here's our terms of our conversation. Why don't I just park and get through this here? Okay. All right, so here's our handshake. Do you see how much we ripped out of a handshake? That's why it's so important to capture them. They tell you everything about the terms of the conversation. Okay, so final act, there's our handshake, and now we start to move our data. Now, keep in mind that because we know the scale factor, Wireshark saw the scale factor for the client side up in the SYN. Any packet that you see, let me just come down here and pick one. From 172.16, okay? 172.16, cool. All right, I just grabbed a packet that was down a little bit. I come down to window size value. This is something that I get asked, not quite a bit, but I'd use the word often. People send me a trace file and they say, Chris, check out the window size. This is a really low window size. What's going on here? Do I need to get in the registry and increase this window size on the client side? In fact, I mean, it happens quite a bit. So window size value is 64. This is what the client is advertising back to the server. But remember that since we captured the scale factor in the handshake, we know he doesn't really mean 64. He means 64 times 256. That's the calculated window size. There's our scaling factor. We caught this. Now, if we miss the handshake, Wireshark's like, I don't know, 64 is what he's saying. I don't have any context for that number. Now, if you miss a handshake, if you did not capture the scale factor, and you're in a TCP stream somewhere down the road, and it says, okay, I didn't see the scale factor, and you see a 64. Pretty simple to figure out if that number is scaled or not. Basically, what you see, what's the next two packets after this ACK? This is data coming in from the server, right? 14 and 15. Those are full-size packets. That's coming in from the server. So again, I'm capturing client side, but by the time this ACK gets to that server, if I legitimately only had 64 bytes, that server is going to go, whoa, hey, God, this teeny little one, I can only send you 64 bytes? Really? Okay. Ding. Ding. Right? Okay, is that it? Right? So when you see data continue in flight the way that we see it here, we know that that number is not the real number. In fact, we can go into our TCP settings and tell Wireshark to do a manual scale factor if we had to. Okay, so we talked quite a bit about this trace. Let me switch up here. I want to go to... Yes.
How come you don't see that calculated window size?
Okay, let me go back there. Oops. I opened up a case study. Let me go back to the same one here. Okay. All right. So first of all, the question was, we see that scale factor in the SYN. So right here, if he's advertising a scale factor, how come we don't see it immediately off the gate, right? We see an 8K window. He's sending a scale factor at 256. Keep in mind that this is just, a SYN is establishing the terms of the relationship. Laying down our ground rules, right? Right now, I don't know yet if the server will let me do this. I'm offering it to him like, hey, so we cool? Could we use this option? So right now, it's not applied. But in the ACK, as soon as I get a scale factor back from him, the third packet in the three-way handshake will apply the scale factor. Right, so this is the ACK, the final ACK. We're cool. Sequence number one, acknowledgement number one, we're synced. Now let's apply our scale factor. So it is applied, but just on the third packets. And the reason, again, it's not in the SYN, is because I don't know if I can do this yet. And if that server doesn't do it, then all I got is 65,535. So something just that I'd like to kind of kick out to you guys as exercises. When you're capturing, when you go home and look at your systems and stuff, what kind of options do you see coming off of your servers? When you hit something, take a look at those options. Tells you a little bit about the stack. Is it a really old stack that can only do certain options? You know, a lot of some traces that I've seen from these IoT devices that are out there, it's interesting to look at the TCP options with some of those devices. They're pretty limited. It's pretty interesting. In fact, if we have time, I'll show you a trace or two of that. But anyway, actually, let me show you one that I had not long ago. Okay, here's my handshake. Okay, we can see what the client is offering. All right, let me come down here. Let's focus down here. So kind of similar to what you just saw. This is a client talking to a server. 39 milliseconds later, we get a SYNAC. So we're going out there, we're sending our stuff. We're starting off all small, 8192. Don't want to commit too much yet until I know what the ground rules are. Server comes back with a SYN. Anything missing? Tell me about this server. What do you learn from this? Let's just look here in the TCP options. We got an MSS, okay. He's doesn't have SAC. Okay. So he's telling me that SAC thing can't do it. No fast retrans. You send me duplex, I'm not going to know what to do with them. Okay. So that's interesting. Window scale. Right there, he's offering me 8192, and he means it. Maximum segment size. Okay, interesting. Kind of a weird number to me, a little bit. But all right, we'll work with it. He's just telling me 1379, that's what I can receive. Now, it's possible. Let me throw out that maybe thing. It's possible that something along the path changed that MSS. All right? He could have sent it at 1460 or whatever number he picks. In flight, a router could have gone ding and kicked it down to 1372 or 1379. That's possible. That's why I can't be absolutely sure what he sent unless I have both sides. But this is what I want you to get used to. When you're looking at these handshakes, spend some time looking at the options. What do you see? What do you not see there? What's missing? It's establishing the rules of the ground rules of the relationship. Okay? Now, if we don't have a handshake, how are we doing? Man, we're just having so much fun. Look at us. Let me just pull. Okay, sure. I think this is one where I missed the handshake, or I was sent it without any context. Okay. I have no handshake here. This is just a single conversation between a client and a server. A big dump of data is going in one direction. Because I don't have the handshake, let me ask you this. Since I don't have the handshake, what do I not know at this point? I don't know my scale factor. Good job. So if I come down here to TCP, calculated window size, okay. Here's the original one. Window size scaling factor, unknown. Wireshark saying, look, missed it, don't know. SAC, I don't know if I can do SAC or not. I could look at the behavior and determine that, you know what I mean? If I see duplex and fast retrans, okay, these guys do SAC. What else do I not know? Maximum segment size. I don't know that. But again, that's something, if I look at my info and I see stuff going in both directions, no retransmissions, okay, I can sort of determine it, right? Okay, but again, those handshakes are important to get. They tell us quite a bit, that initial round trip time. It lets us have a good picture of what's going on in that conversation. All right, so, you know what my problem is? I'm just used to having more time with you guys. That's my issue. Because like usually when I'm doing Wireshark training, I got like 3 full days, like, hey, let's shred, but 4 hours. Okay, sequence numbers. This slide came about because I was chatting with a few of the attendees over the past couple of days, and they just said, you know what, again, think one fin, right? We're just reviewing some of the TCP stuff. Doesn't mean that, you know, it doesn't mean there's a problem. It just means, hey, Let's go back over sequence numbers, how those work, and how we can make sure we understand what they're doing. Because in session number 2, that's when I'm going to start getting away from the fundamentals and start going into case studies. Then you'll need to do some of this in your brain. So let's go back over sequence numbers and how those are counted. Okay? Let's go to this next trace. Okay. Same trace. Oh, no. Oh, same as the first one. Okay, so sequence numbers. We've already talked about in the handshake how one ghost byte of data is exchanged. It's not true data, it's just a ghost byte. It's just to increment the sequence numbers on both sides. That is exchanged in the handshake, all right? So if I come over here to my, if you look at my sequence number, sequence ACK. So my sequence number, my starting sequence number is always 0 in that, well, Wireshark clears it to 0. I send my SYN, the receiver ACKs 1, he sends his 0, and then I ACK 1 to him. So we basically sync up and start with sequence number 1, ACK number 1. If I come down here to the first actual packet with stuff in it, going from the client to the server, you see 1514, that length of packet? All right, this one actually has stuff in it, length 1460. Okay, let's take a look what happens to the sequence numbers here. Now, just so you know, if sequence numbers and acknowledgement numbers, if they're confusing to you, this is absolutely something that I definitely suggest you walk through again and again, back up, do it slow, start from the SYN. My poor wife, when I'm doing sequence and acknowledgement number analysis, it looks like all these numbers everywhere on my desk, and I'm like just writing these numbers down, and especially tracking down a SAC thing, and she comes in, looks at my desk, and she's like, okay, I'll just leave him alone. I know what not to throw away. Okay. All right, so first real packet of data. This is where the session is starting to be actively used. We start on sequence number 1. Client is saying, this is a client request that's going to the server. He's starting on sequence number 1. I'm sending how much data? Exactly, 1460. That's how much I am sending to that server guy over there. Okay? My next sequence number is sequence number I'm starting at plus amount of data sent. This is my next sequence number. Since I'm not yet on that packet, I'm still at 1. So as soon that Wireshark sees that 1460 I'm sending, and it suggests to me the next packet in this direction will begin at 1461 unless there's a problem. All right? I don't yet have an ACK. It's just the next packet. Now you can put all this stuff in columns and stuff. I don't do that to you on purpose. Just because unless you're used to my columns and you built it out yourself, it can be more confusing than helpful. Sequence number, notice the one that we're starting off, 1461. Okay, so we're 1460 bytes into this packet stream. Now I'm starting at 1461. I am sending how much data? See my length right there, 61. That's how much data I am actually sending, or TCP segment length. Okay, so my next starting sequence number will be 1522. That's where I'm up to. When I begin a new packet, send any data that way, that will be my sequence number that I start from. However, in this case, the client sent those 2 packets, one full one and a little bit of residual, and that was the get. That was the request that it was sending to the server. Client pauses, doesn't send anything else, don't need to, I sent my get. Server comes back, let's take a look at him. He's starting on sequence number 1. We established that in the handshake, sequence 1. Next sequence number is also 1. Why? It's an empty ACK. Look at my TCP segment length, 0. Server's not sending anything. Wait Wait a second, server, I asked you a question. You telling me you're not sending anything? We'll get there. Sequence number 1. Next sequence number 1, empty ACK. I'm not sending anything. However, look at my ACK number. Acknowledgement number 1522. I'm ACKing what you sent. This packet is a very important packet when it comes to application analysis. Why? This packet tells me that server got my request. It got there. He ACKed 1522. If I don't get this ACK, what am I going to do as a client? Going to wait some amount of time, and I'm going to retransmit. What, he didn't hear me? This ACK, I just personally call it a hush packet. All right? The server got my stuff. My stuff is there. My get is being processed. He's going and doing whatever he's got to do on his side, and I'll just hang out. Now, in this trace file, how long do I wait?
40 seconds.
I wait 20 seconds. That's the next thing I hear coming back from that server. Is that the network? Network client server, what do you think? The server. Now, again, I'm capturing client side. Can't be 1,000% sure. Won't bet my firstborn if I had one. But on that side over there, if I had that capture, that's a number I'm going to look for. Okay, so that first packet, that ACK, okay, good, I got your stuff. TCP at that point, packet number 6, TCP can't do anything until Mr. Layer 7 up there drops some data. Boom, got it. Boom, here you go. Server-side TCP is like, I got you, hang on. Oh, boom, right? So server-side TCP, he did all he could do. This is application stuff. Let me show you, this was actually a fast response from this server. I'm going to show you, do I have time? Oh, I got 2 minutes. I got 2 whole minutes. Woo! Check this one out. This is how bad it got in this specific case. What do you see, people? Okay. Sin-Sin-Ak-Ak. What's my round trip time? 97. Actually taken from the same 2 stations, so I won't show you the IP TTLs. Sin-Sin-Ak-Ak. We got our request. That first big packet come from the client, packet 4. Big request. Full packet. Residual stuff coming in packet 5. Server gets it. Packet 6, 106 milliseconds later, server acts back with 1496. If I looked at the sequence numbers, that's probably exactly what that client sent, right? We see the 1496 in the ACK from the server. That number right there, ACK 1496, woo. Then what happens? Okay, we wait, packet 7, 45 seconds. Client says, we still there? This is from the client, right? 192.168 going to 10. 10's the servers, 192.168's clients to me. That's just how I work. 7, okay, so this is an empty packet. It's called a TCP keep alive. That's a timer. Basically, the client's saying, look, I got to go. I got stuff to do and resources to free up. So are you still even there? Because I sent that request to you. You said you got it. I've been waiting 45 seconds over here, and you're not saying nothing. Client says 99 milliseconds later, which is pretty close to our network round trip time. Server, rather, says, keep alive ACK. Yep, I'm still here. No data, but I'm still here. TCP is still up. We're still talking. Let's keep this thing alive. Client waits another 45 seconds. Checks back in. Hey, server, what's up? I sent that request to you. You said you got it. Are we still talking, or can I just kill this thing and we'll just be done with it? Server comes back 99 milliseconds later, or 95 in this case. Yep, I'm still here. So the two TCPs, layer 4, they're good. They're chatting, they're talking. Now Wireshark in this case, this one was sent to me because the poor client's like looking at these black lines and red letters and going, oh my gosh, oh, the network's exploding. Wait a second here. TCP keep alives. They're just keeping this connection alive. That's not a problem. The problem is that on the server side, that TCP is just waiting. Like, how long does it wait? Well, you see 18 seconds after that second keep alive. Let me just, I'm just going to come up here. The last packet of request, I'm going to start our timer over. Set unset time reference. I can actually pull this out a different way in my HTTP profile, but basically, you see your little arrows that Wireshark helps you out with? You see the arrow that went to the server? And this is the response from the server in packet 11. We waited 108 seconds on that server to respond. And these guys actually waited that long. They went to this tab, hit the tab, and then go get coffee. Come back, they got their stuff. And some people sat there and just spinny wheeled for a long time. And of course, who is getting blamed? The network. Let's go from 1 to 10 gig to the desktop. Wouldn't have done a whole lot. Right, so next step from here, and I'm going to go ahead and leave us on a break right now after saying this. At this point, from the client side, all I knew is I had 108 seconds of application delay. To figure out what was going on, I would have had to move to the server and figure out, okay, this request comes in, what does that server do next? Does it legitimately wait and do nothing for 108 seconds, or does it go and talk to some other server and get some other tertiary data? Okay, guys, this was TCP Fundamentals. Coming back in 15 minutes, we're going to pick up again with a bit more on congestion window, a bit more on receive window, and then some case files. So come on back if you would like.